we have been talking about sets and so on, and then we introduced this notion of the power set, right? And remember, what is this? This is just the collection of all subsets of a given set. Okay? So given a set, its power set is a collection of all possible subsets. Okay? Including the set itself. So remember, there are always two elements that are in this power set, which is the empty set and the whole set. Okay? Then, if the set has more than one element, then there will be other stuff. Okay? And we also figured out that if the set is finite, then we didn't figure out, we actually saw it. We're gonna prove it later. That if you have a finite set with cardinality n, if it has n elements, then its power set is going to have 2 to the n. That's the number of elements. Okay? If it has 4 elements, then the power set has 16. If there are 5 elements, the power set has 32. Okay? And we developed kind of a strategy to systematically write down the elements in the power set. And then we came up with this little formula that was the number of subsets of a set. That's just the cardinality of the power set, so that's 2 to the n. And then if you are asked the number of proper subsets of a set, you have to do -1. That's because you need to remove the entire set, okay? Because you want them to be proper. And you have stuff like this going on in the home. All right. And then the last thing that we're doing was this statement, this claim that says that the power set of A given two sets A and B, the power set of A is a subset of the power set of B if and only if A is a subset of B. And we were in the middle of proving this, okay? So we did one direction. This is a biconditional. When you have a biconditional, you need to prove two statements, okay? You need to prove the conditional and its converse. You need to show both, okay? P implies Q and Q implies P. You need to show that both of those are true. So here we did one direction saying if the power set of A is a subset of the power set of B, then A is a subset of B. We did that. And then I asked you to think about the other way, okay? If A is a subset of B, then the power set of A is a subset of the power set of B. Okay? So I ask you to think about it. Let's do it now. All right. How do I start? This is usually one of the issues that you guys have. That you have a problem in there and then you have no idea how to write the first line. So let's make sure that we understand this. What should be our first line? So how do we begin? It's always the same. What type of statement is this?
P and Q. Assume P and prove Q.
Exactly. So how do we begin?
Assume that A is a subset of B.
Exactly. Do you understand it? It's always the same thing. If you have P implies Q, you assume P, and then you worry about proving Q. Yes? So you see that as if then, okay. Assume this guy, prove the other. Okay? So I'm gonna begin by saying assume that A is a subset of B. Okay, so when we have this for granted, so we're gonna use it whenever we need it. Okay. Now this is not part of the proof, but it's helpful to write it. It's always helpful to write what you want. So we assume that A is a subset of B. Now what is it that we want? What is it that we need to prove? So we want to prove this. Okay. Eventually, we want our last line in our discussion. We want our last line to be this. Therefore, this is subset. Okay, this is what I have to write at the end. Now it's good to write it in the corner so that you see what is it that you need. Okay, now start thinking about to prove this, what do you need to do? So you will get this if you have what? What would allow you to conclude this? In other words, how do you prove that something is a subset of something else?
Three elements in the first one is the second one.
Exactly, the definition. So how do you prove that this is a subset of this? Take an element here and somehow argue that that element has to be here. Yes? So I can prove this if I show that every element power set of A is in the power set of B. Right? So I'm going to focus now my attention on this statement. I want to show that this happens. If this happens, then I will be able to deduce this. Remember, this is something that you do in a little corner. This is not part of the proof. Okay? That's why I use a different code. Now, after this assumption, now what should be my next line? Because I'm going to focus on this. Now I'm going to start assuming that I have an element here, and I'm going to work my way to see if I can argue that that element must be here. Do you understand this? Because remember, if this has First of all, this is always non-empty, so there is an element here. Because if this is empty, then this is always true, right? But this is never empty. Even if A is an empty set, what's the power set of the empty set? No. The set containing the empty set. The power set is never empty. Okay? Because remember, the empty set is a subset of everybody, including of itself. All right? All right, so now my next line will be, okay, so I want to take an element in the power set. I want you to tell me what should I write here. I want to write here. I want to write this. What should I write here?
X.
Okay, I'm going to write X. But what is X?
An element of A on the set as subset.
X is a subset, so be careful. If I write this is confusing. Because I used to write little x for elements, right? But the elements here are what? Sets. So it's more comfortable if you actually write like a capital letter, like S, okay? Just because to stress the fact that the element, we know what the elements are here. We still write is an element of, but if you write this, it's confusing. This is not an element A. This is an element in the power set. In other words, this X is really some set S. Yes? So might as well put it right here. Okay? Let S be an element here. It's okay if you write little x, but you need to understand that's not an element, that's not a traditional element. That's a subset. It's a set. Okay? So, anyways, that's just a technicality, but it allows you now to proceed nicer. Okay, so I begin, this is my second line. We assume this because of that. Now, when I prove this part, to prove an inclusion, inclusion, this is a containment. This is a subset of this. To prove a subset, what you do is begin with an element on the left and somehow argue that that element also has to be on the right. Because what it means to be a subset, right? Okay, so let S be an element in the power set of B. Now we start. Then what can we say? From here, what can we deduce? For sure.
That's a subset of A.
Very good. Why?
Because the definition of power set.
Exactly. That's the definition of power set, right? The definition of the power set is telling us that the elements here are the subsets of A. So if S is an element, then S is a subset. Yes? All right. So now, how do we... So by the way, now looking ahead, remember, we want to show that every element in the power set of A must be an element in the power set of B. So if S is in the power set, what I want to say somehow, I want to somehow arrive to the conclusion that S is an element in the power set of B, right? This is the goal. That's what I want. Now, to be able to say this, what do you need to say? Or what do you need to have? That S is the subset of B. So that's what you have to focus on. Okay, this is what I have so far. Now, how can I use this to argue that then S is also a subset of B?
Well, you were assuming
that
A is a subset of B, therefore subset of A is a subset of B.
Very good. So, but we need to prove that little lemma. In other words, the transitivity of inclusion. If A is a subset of B and B is a subset of C, what can you say about A and C?
Subset of C.
It's a subset because every element in A is in B, but if every element in B is in C, then every element in A is also in C. You understand this? So let's prove that little lemma and then we use it. Because we see that we're going to need it. But you see how you always should have in your mind what you want so that you can get ideas of what you need to do to get there. Otherwise, if you're just blank, you don't know what to write. You don't know what to say. And don't force anything. Remember, you can only work with what you have, okay? So we have this. Now, thinking about it, okay, somehow I want to argue that this is a subset of B. How? Well, it's a subset of A is a subset of B. We can hopefully see the relation there, okay? But let's prove that little lemma. So lemma, now this A, B, C have nothing to do with the stuff above, okay? So let A, B, C be sets with, so the statement is, let's say A is a subset of B and B is a subset of C, then what can we deduce from here? Then A is a subset of C. You understand this? All right, let's prove this. Again, how do we prove this? So we already have this this condition. So we know A is a subset of B and B is a subset of C. Okay. So if you want, you can say assume A is a subset of B and B is a subset of C. So we have that. Okay, that's given to us. Now we need to prove the then part, right? So we need to prove this part right here. So how do we prove this? It's the same thing as before. How do you prove that a set is a subset of another set?
Every element in A is in C.
So how do we start?
Let X be an element in A.
You know, don't block yourself. It's always the same thing. It's the same thing. Let X be an element on A. Now we want to do some stuff, and eventually we want to deduce that that element has to be in C. Now, how can you fill in the blanks in here? Starting with an element in A, how can we argue that that element is in C? And looking at the stuff that you have.
The same element is in B.
It's in B. Why?
Because A is a subset of B.
Good. And now we have the element in B. Then what can you say?
It's in B, it's in C.
Why?
It's a subset of C.
Because B is a subset of C. Done. You see? So start with X in A. So then X is in B. Because A is a subset of B. Yes? But if X is in B, then X is in C because B is a subset of C. Do you understand this? So we basically are using the transitivity property of implication, right? If P implies Q and Q implies R, then P implies R. That's basically what we're doing. Okay? So that's a little proof. So now we can use it because remember, you cannot claim something without first either we did it in class and we prove it as a theorem, or you have to prove it yourself. Like here we're trying to use this claim, so we need to prove it because this is new information. Anyways, now you know if you have three sets and then they have this nested inclusion property, then you have the transitivity that if A is subset of B and B is subset of C, then A is subset of C. And that's exactly what we're going to use here. Because now we know that S is a subset of A. But we know that A is a subset of B, right? So what can we now deduce? So now from here, we can deduce that S is a subset of B. And the justification is, well, the lemma that we just proved before. Or below, I should say. Yes? The lemma since A is a subset of B. Okay? All right, and now hopefully you see how to unwind this. We have, remember, why do we want it to get here? What should we say now? If S is a subset of B, what can we now say? Remember what you wanted? You want this. So you started with this. What do you want to end up with? S is an element where? The power set of B. Do we have enough evidence to say that? Yes, we do. S is a subset, so it's an element in the power set. So now we can say that S is an element in the power set. Again, that's definition of the power set. So therefore, we just argue that if you start with an element in the power set of A, that element will end up in the power set of B. So we just argue that the power set of A is a subset of the power set of B. And now this finishes the proof. Questions? Yes?
So you didn't start with every element be A or finish in that. You didn't use it at all.
What do you mean? Oh, no. Remember, this is not part of the proof. This is what is in your mind. I mean, this is your guide. To get this, I need to do this. In other words, I need to show that if you have an element here, it has to be here. That's what this is saying. And that's what it did, right? We start with an element in the power set of A, and then you want to argue somehow that that same element has to end up in the power set of B. If you manage to do that, then you're good to go. Yes? All right. Questions? Okay, so that was the power set. Let me introduce to you another operation that we do, which is called, so another way to form new sets. So the power set is how you can get a new set out of a given set, okay? Now another one is what we call the Cartesian product. So it's the product of two sets, okay? And this is the formal way that we actually use to make tuples. Like for example, if you in college algebra, pre-calculus, and calculus, you work in R2, which is the Cartesian product of R with itself. Points of the form x comma y. That's what you obtain as a set when you multiply the real line together. When you multiply with itself. And now we're going to formalize that idea. Okay, so let me write down the definition. So definition. Let A and B be two sets. Then the Cartesian product of A and B. I'm going to write in words and then I'm going to put it in symbols. So is the set of all ordered pairs with the first element in A and second element in B. So in other words, the notation is this one. So notation, we write A cross B. So that means Cartesian product. So I mean we're taking the Cartesian product A and B, and then here is the definition. I'm just going to rewrite what I say in word in set notation. So it's a set of ordered pairs. So these are elements of the form A comma B, such that the first element is in A and the second element is in B. Okay, so this is the symbol for Cartesian product. This means Cartesian product. And the rest of the symbols you know, right? You know the such that and you know the and. Okay, so if you have two sets, you can always make the product, and it's just a collection of all possible ordered pairs that you can make, where the first guy is taken from A and the second guy is taken from B. Okay, that's what it is. So let's see. Let's do a little example. Let's say that A is a set 1, 2, and B is a set 2, 3, 4. Okay, so find A cross B. All right, so let's see, what would be A cross B in this case? Again, we have to find all possible ordered pairs where the first element is in A and the second element is in B. Here, the easier way to do this is just do it one by one. So start with an element in A, then find all pairs with that guy, and go to the next one and repeat. Okay? So for example, A has two elements, 1, 2. So let's begin with 1. So all pairs that we can make with 1 in the first position. So what are they? 1, 2, 1, 3, 1, 4. So remember, what you write here in the second spot, it has to come from B. Okay? It's an ordered pair. So this is all the pairs that you can make with 1 the first position. Now go to the second element and repeat. So what are all the pairs that we can make? What are they? 2, 2, 2, 3, and 2, 4. And then that's it, because we don't have more elements of A. In other words, for each element of A, we have these many pairs, right? The size of cardinality of B. So just by looking at this little example, what can we say about the cardinality of the product? What's the cardinality of A cross B? In this case, it's 6. So, okay, 6. So, in general, what do you think it is? Notice that 6 is 2 times 3, where 2 is the cardinality of A and 3 is the cardinality of B. Because what I told you, for each element of A, you have these many pairs, right? So how many pairs do you have? The number of A times the number of B. Yes? If A has 2, then there are 6. If A has 4 elements, how many elements do you have? For each element in A, you have 3 pairs, so that would be 4 times 3. It's 12. Understand this? So if the set, this is only the sets are finite, okay? So in general, the cardinality of A cross B is going to be the cardinality of A times cardinality of B. This is called provided that if A and B are finite. Okay? If they are infinite, it's a whole different story. But again, we'll talk about cardinality for infinite sets later on. First, we need to discuss functions, so that then we can talk about, so that then we can deal with infinite sets. Okay, questions? All right, so we have that little, if you want, it's a little theorem, and we're gonna use it when we talk about counting. This right here is what we call the multiplication principle. Okay. All right. So I guess let me give you another notion. So note, if A equals B, okay, then A cross B, of course, will just be A cross A. And for this case, we have a special notation. Guess what that is? How do you think we write this?
A squared.
A squared. But you need to understand that when you write this, this is a set, right? So this means Cartesian product of a set with itself. In other words, these are all ordered pairs that you can make where the first and second element are coming from A. Okay? For example, the plane, the Cartesian plane, is R2. So, example, the Cartesian plane, you know, the one that you use to graph all your functions in college algebra and so on, your x and y, we call it that's called Cartesian coordinates or Cartesian plane, is obtained by doing, you know, is the set of ordered pairs x comma y, and what's the condition? Both x and y are real numbers, right? So x is a real number and y is a real number. That's a Cartesian plane. And then we write it as, instead of writing r cross r, we typically refer to it as R2. Okay? In calculus 3, for example, you work in R3 because now you have 3 dimensions because you work in the space. Okay? You have triplets, X, Y, Z. Okay? But then you can talk about R4, R5, R20, R whatever. Okay? Now, whether that has a physical meaning or not, that's a different story. It has a meaning mathematically, but you know, in reality, we can only see up to R3. People can argue R4, you know, 4th dimension, time, whatever. But that's another story. I don't understand that, so I don't get that. Like the physics of it, I don't get that. I think we can go up to 12 or 16, like doing some weird physics, but
That sounds fine.
But in math, you can go up to whatever you want. I mean, Rn is just, you know, R plus R n times. That's what it is. Okay, it's a tuple with n entries, and then each entry is a real number. So we can do math on it, and we do math on it. So the version of calculus, so we typically do calculus in R2, R3, but really the calculus that you do in R3 is the same as the one that you do in Rn. Okay, that's called multivariables calculus. And for some reason, we always specialize only in 3 variables just because it's easier, but the same ideas then they go in general, but then you need to know more too. For example, you need to know linear algebra if you want to be able to do calculus in more than 2 dimensions. To really do it, you need linear algebra. You need matrices and all that stuff. Okay, so that's the Cartesian plane. So the point is that when you want to do a product of a set with itself, we have a special notation. So in fact, we have the notion of an, right? And this is just a cross a cross a, and this is just the product n times. So what is this? This is the set of tuples of the form a1, a2, an, such that for all ai is in a. Right? That's what it is. So it's just, you know, tuples, ordered tuples of n numbers or n elements where each element they are all coming from it. That's what that means. Okay, questions? All right, let me do another example here. Example, show that A cross B, of course here, when I write this, even if I don't say A, B, and C are sets, okay? Show that A cross B cross C is not the same as A cross B cross C. In other words, there is no associativity when you do Cartesian product. Okay? So if you do A plus B plus C, show that this has nothing to do with this. How would you go about justifying this?
One would be A1, A2, A3. The other would be like a set of A1, A2, close that, and comma A3.
Very good. Remember, I mean, this is a set and this is a set. Yes? What does it mean for two sets to be equal? Like the opposites. What does it mean to be equal? They have to have the same elements, right? So if you somehow argue that the elements over here have nothing to do with the elements over there, then that's it. They are different, right? And indeed, how do elements here look like? So how does elements in the set A plus B plus C look like? They are triples, right? They are triples, A, comma, B, comma, C, where A is in A, B is in B, and C is in capital C. Yes? Those are the elements that they are triples in particular. So triples. You say triples or triplets?
I don't know which.
Huh? It depends.
Yeah.
So here what?
You're using tuples and triples, I guess.
Then triples, yeah, because n tuple, so triples. You could also say
Three.
this is a triplet.
Triplet, I guess, would be the informal.
The informal.
Yeah.
You can just say 3.
So those are the elements here. Now, how do the elements in the other set look like? So A plus B plus C. How do elements here look like?
Duplet of duplet.
They are pairs. They are ordered pairs, right? Remember, now it turns out that the first pair has to be, let me put a question mark here. The first pair has to be an element in A cross B, right? So how does it look like? It's an ordered pair. So that first pair is an A comma B, yes? And then the second element has to be in C. So where A comma B is in A plus B and C is in capital C. So notice the difference. An element here is a triple, an element here is an ordered pair. This is a pair. Now, it turns out that this pair, the first element, is another pair. But this is completely different to what we have here. Do you understand this? Points are different than pairs. I mean, numbers are different than pairs. This pair could be read as a point. If all of this is R, then this is a point, comma, a number. This is a number, comma, a number, comma, a number. Two different things. Do you understand this? Yes.
So the parentheses, what denotes that?
The parenthesis is telling you that if you put parentheses, then you change completely the meaning of this. In other words, there is no associativity. Remember, when you're going to see when we introduce other operations, for example, if you use OR, if you have P or Q or S, you could do it like that, or you could do P or Q or S, and it's the same thing. Or you could do P or Q or S, and it's the same thing. You know, so the OR operator enjoys this. This is called associativity. Just like the addition operation enjoys associativity, the product operation enjoys associativity. So OR and they are associative. Now, this new operation that we're introducing is not associative. In other words, if you put parentheses, you have to be careful. You need to really mean to have that parenthesis there. In other words, you need to really mean another pair, comma, an element. Okay? Because if you don't mean that, then you are changing the element completely. So they are different because their elements are distinct. So the elements in each set are different. So the sets are different. I mean, I'm justifying the question, okay? And why are the elements different? Well, the two lines above justify. One has triplets, triples, the other one has pairs. Do you understand this? So, for example, it's just that it could be confusing because you're looking at the A, the B, and the C, but you may want to think about it as like black boxes, okay? The first one looked like this, something, comma, something, comma, something. And the second one looks like this, something, comma, something. They said you don't know what is inside that something, but that's how they look like. Now, when you uncover this, then you see A, B, C. When you uncover this, then you see A, comma B, and C. But if you cover the first layer, this is what you see. Clearly, they are not the same. Okay. All right. Questions? You okay with this? Okay, so that's Cartesian product. And I guess the last thing that I want to do, let me see. I think is okay. Let me quickly introduce the notion of truth sets. So there is this idea of truth sets of quantifiers. So truth sets and quantifiers. Let me just write the definition. So let's suppose that we have a proposition. So let P of X be a proposition. Now X here, I'm saying X, but it could be X, Y, or whatever, okay? So let P of X be a propositional function. Be a propositional function. Then its truth set, so its truth set is the set of all values of X that makes P of X true. Okay? Is the set of all values of X that make P of X true. So i.e., so in set notation, the true set of P of X is the set of all X in our domain, in D, so the propositional function with domain D. Remember, we need to have a domain when we talk about these things. So all X's in the domain such that P of X is true. I mean, formally, I don't really need to write is true. If I say such that P of X, is implied that I mean such that P of X is true. Okay? In other words, it's just the values in your domain that makes the propositional function true. Okay? We call this the truth set. For example, every time that you solve an equation, you're really finding the truth set of the corresponding propositional function. I'll give you an example. For example, imagine that our P of X is the propositional function absolute value of X equals to 1. What's the truth set here? What's the truth set? To find the truth set, you really need to solve this equation. So here in the little corner, you do your little algebra. What are the solutions to this equation? X equals 1 or negative 1, right? There are two solutions. Of course, it's understood here the domain is real numbers, okay? So what's the truth set of this propositional function? That's the set of all X such that P of X is true. But hey, this is really just 1, negative 1. You understand this? So in college algebra, you used to call it solution set. Now that you know logic, we call it the truth set of a propositional function. What? This is your propositional function. Remember, an equation is a propositional function. This is not a proposition because we don't know what X is. Once you give me X, then it becomes a proposition because you can't tell whether it's true or not. So let's see, let's practice some algebra. I mean, this is just to, I guess, to make a point. So how about, okay, let's make it a little bit fun. So how about x squared plus 2x plus 3? What is the truth set of this? What do we need to do? And solve the equation, right? Solve the equation. Okay, let's make it easy because otherwise I have to put the formula and all of that. So let me change it and let me do 4 here. No, let me put a 3 here and then 2. Let's just do the easy one. I mean, I just want to show you that every single equation that you have solved in any other classes can be translated into a truth set question. Okay? I made that propositional function, and then the question is find the truth set of this. Okay? So here we really just, to answer the question, we just need to solve this. Wait. So we really want to figure out what values of x makes this equal 0. Okay, so factor, that's x plus 2, x plus 1. So we know the solutions are -2, -1. So here the true set is a set -2, -1. Because those are the values that makes the proposition 2. Do you understand this? And as our last example, again, domain here, let me specify the domain is the real numbers. And let's say our p of x is x squared plus 1 is different than 0. What's the true set in here?
All real numbers.
Or real numbers. So, the true set can be the whole entire domain, right? In other words, that's like saying for all x, p of x is true. If that's a true statement, then that means the true set is the whole real, is the entire domain. You understand this? And then on the other side also, what if I now say q of x is x squared plus 1 is 0?
The empty set.
Then the true set here would be the empty set. So the true set could be empty. In other words, if when you do the existential, it's false. Okay? So it's equivalent to say that there is no x for which x squared plus 1 is equal to 0. Okay? So, the true set could be the whole thing, the empty set, or something in between, as we saw in the previous example. Okay? All right. Questions? So, technically, every other thing that you have learned in your previous classes can be translated in terms of this type of question. Okay? All right. So, questions about what sets are and these basic notions that we have discussed so far. No? All right. So now, as usual, when we introduce a new object in mathematics, we like to develop operations that we can do with these objects. Okay? How do they interact with each other? So we have discussed power set. We have discussed Cartesian product. Now let's talk about the other common operations, which are union, intersection, complement. Okay? Let's talk about those. Which I assume that you already know these things, okay? Or if you watch the videos, you already saw them. But now the question is, do you have practice? Do you have practice improving statements about this relationship? That's really probably gonna do that next time. But at least now let me get the definitions down. Okay. So operation on sets. So in all of this discussion, A and B are gonna be sets. So let A, B be sets. Okay. And capital U, I'm gonna use it for the universe. Remember, universe and domain, these are interchangeable things, okay? So this means this is the place out of which I'm picking my elements to make the sets, okay? All right, so the first idea that I wanna talk about is the union of two sets, and then I'm just gonna give you the definition, okay? So the union of A and B, this is the notation that we use. A, we use a capital UB, and then the definition is, this is the collection of all elements that are in A or B. So these are elements X in the universe, such that X is in A or X is in B. The operations that I'm going to tell you here, they always have a counterpart in logic, okay? Union goes hand to hand with OR in logic, if you think about it, okay? Now, the one that corresponds to AND would be intersection, and the one that corresponds to NOT, the negation, is the complement. Okay? All right, so A union B means all elements in the universe, so is that X is in A or X is in B. Now, let me give you, every time that I give you this, I will show you the Venn diagram, so you have some visualization in mind. So again, remember, Venn diagram, we draw a box here. This box represents our universe. And then I'm gonna draw A over here. Now I need to draw two diagrams for you. Okay, this is one possibility, but then there's another possibility. What would be the other possibility? They don't have anything in common. So A is somewhere in here, and then B is somewhere over here. So they have nothing in common. Okay, the union basically says just put everything inside and make a bigger set. Okay, imagine that you have two bags. You get a bigger bag and you dump everything inside that bigger bag. That's what the union is. So the Venn diagram I mean, the set that we're describing, A union B, is what you see shaded here. And I shade everything because it's anything that's in A or B. Remember, a Venn diagram means you do the little circle, the stuff inside the circle belongs to that set, what's outside the circle does not belong to that set. Okay? So the union is what I have shaded here. This is A union. Depending on the situation. Either if they have something in common or not, doesn't matter, just put them together. Questions? All right, so let me see. Let me define intersection and then we're gonna do one example. The second intersection of two sets. So the notation is A, an upside down U, B, same way that AND is an upside down OR, right? An upside down V, the intersection is an upside down U. And then these are all elements X in the universe, such that X is in A and X is in B. In other words, the common elements, okay? The elements that both A and B share. So if we were to do the Venn diagram for this, we have a universal set here. This is A, this is B. Then what would be A intersection B? It's going to be this part right here, the common part between the two. Do you understand this? So note, if A intersection B is empty, what does that mean? When we say that the intersection is an empty set, that means that then A and B have nothing in common. They have no common elements. For example, the picture is this one, like the one that I draw above. If this is A and if this is B, then you don't shade anything because they have nothing in common. Do you understand this? There's no overlapping part. We have a name for this. When this happens, we say that the sets are disjoint. Okay? So we say, this is the definition of the word. We say that A and B are disjoint. Okay? So the definition of disjoint is that the intersection is empty. They have no common elements. That's what that word means. Okay? All right. Questions? Okay? So here's an example for you to try. So first, show that, let's see, what do you think? If I have the set A and I have the set A union B, what do you think I should write in between? What do we put inside this box? What symbol makes sense to write? Among all the symbols that you know. For all. Doesn't make sense. For all is for you know, when you have predicates and stuff. These are sets. So what symbol do you know about sets? You know the equal symbol, the subset symbol, the proper symbol, the Cartesian product symbol. You know several symbols now that allows you to have sets on the left and on the right. Which one do you think is should be? I'm asking you to show that. So what should I write here? What do you think makes sense? What does your intuition says?
Subset.
A subset. Why not proper subset?
Because it can be equal.
Eh?
It can be like equal.
Why?
Because A is and
when would they be equal?
they're the same one. Like A union A.
If A is equal to B, right? Or if B is an empty set. In other words, if there's nothing, if B doesn't have anything to bring to the table, you have a bag full of stuff and an empty bag. When you dump everything in a new bag, this bag doesn't give you anything. So you just get what you had originally on this first bag. Yes? So anything, that's actually a law. Anything union the empty set is that anything. Okay, A union the empty set is A. Okay? That's like when we said P or false, P or true, or actually P or false. What is this? P. That's P. Why? Because false doesn't bring anything to the table for this OR statement. That's like the empty set. Okay, so the exercise is to prove this, that A is a subset of the union, of A union B, and then second one is show. Now, what do you think would be a similar statement for intersection?
Intersection is a proper subset of A.
But don't say proper, because again, if the sets are the same, then they'll be equal. So that A intersection B is a subset of A. Or you could also say B here, doesn't really matter. Okay? So the exercise is to prove this. If you were able to tell me this, it's because you already know how to prove it. Right? And now look at it, and then hopefully it makes sense what the statement is telling you. So see if you can write a couple of lines arguing this. Let me take attendance in the last minute of it. So again, here what we're really looking for is, do you know how to begin and do you know how to finish your proof? So let's see if you can successfully write your first line in the proof. Remember, it's the same thing always. Okay, do you know how to start the proof, correct? Just one line.
Let X be an element in A.
Right, you want to show A is subset of, it's always the same thing. So let X be in A, then what do I say? Then, now here you have to be clear. If X is in A, what can you say?
The set A is the set A.
Then X is in A or X is in B. I don't know if X is in B or not, but because now here we're using our knowledge of logic. If you know P, you can do P or whatever you want. Yes? This is a rule of inference. We know this is true, so then this is also true. Do you understand this? We already know this piece is true, so I can attach to it whatever I want as long as I put an OR. Yes? You know, it's like saying when you have 0 times blank equals 0, are you free to fill in here whatever you want? Yes, right? That's exactly that. If I already know this is true, you can fill in this part whatever you want. Okay, I'm going to fill in what I need. I need to have OR X in B, so now I can say, you know, and this is since X is in A is already true, so I don't care what happens in B. But now I can say that this means that X is in A union B. This is definition of union. Yes? Now, on a similar note, how do you prove this? Let X be in the intersection, right? Start with an element in the left, show that it's on the right. Now, what does this mean? This means that X is in A and X is in B. What did I use here?
Definition.
I use the definition of intersection. Yes? Now, what can we deduce from here? Remember, when I write these things, what I'm saying is that this is a true statement. Now, you can use another rule of inference. What does it say? If you have P and Q, you can deduce P. Or you could deduce Q, whichever you want. Here, because this is true, that means these two guys have to be true. In particular, this better be true. Right? Then X is in A. So here, whenever you do this at this point, you can just tell me this is a logic step. This is because of logic. You see? Because we know this is true, then I can deduce that X is in A. That's because of logic. But then, if X is in A, that's exactly what we want, right? So we started with an element in the intersection, and we showed that it's in A. So the intersection is a subset of A. So many of these exercises is just 2 lines. The question is, do you know how to write those 2 lines? You see, it's not really as complicated. It's just, can you put this formally this way? Okay. All right. So, okay, that was good. So with this, you can do, I think, a big amount of the homework. There's still some examples about surveys and things that are in the homework. Then probably on Monday, I'm gonna do at least one, so you see how this goes. But then I'm gonna start with the next topic after that. Okay. So I'm gonna leave you Friday to keep watching the videos if you haven't watched all of them, and keep doing problems. I will be extending the home. Okay, let me stop.